All right, so today we're diving into some pretty heavy stuff, at least for me, maybe not for you. Intuitionistic logic. Uh, as a philosopher, I think this is one of those areas that really kind of shakes things up.
Oh, absolutely.
Really kind of makes you question some assumptions.
Yeah, for sure.
So we're starting with the Stanford Encyclopedia of Philosophy on this one, right?
We are. And one of the key things that they highlight right off the bat is how intuitionistic logic really diverges from classical logic. And they use the law of excluded middle as a way of kind of showing that.
Yeah, the law excluded middle. It's either raining or it's not raining.
Right, exactly.
But how does intuitionistic logic approach that differently?
So in classical logic, the law of excluded middle, it's applied universally, right?
Right.
But intuitionism kind of says, wait a second, like what about situations where we're dealing with infinite possibilities? And so a great example of that is Goldbach's conjecture, which states that every even integer greater than 2 can be expressed as the sum of two primes. Now, we don't have a way to definitively prove that statement or its negation,
Right.
and so intuitionism kind of acknowledges that.
So instead of saying it must be true or false, it's saying, well, maybe we don't know yet. And that's
Exactly.
okay.
Yeah, it shifts the focus from abstract truth to what we can actually show or construct a proof for.
And that has implications, I'm assuming, for like all sorts of things. Like what? Give me an example.
So one of the examples is in proof by contradiction. So in classical logic, you can assume the opposite of what you're trying to prove. And if you reach a contradiction, then boom, you've proven your original statement. But in intuitionistic logic, this only works for proving negative statements. You can't just use that not and have it work out the same way.
Okay. Yeah, so that kind of throws a wrench into things a little bit.
Right.
I'm assuming that also has implications for like how we even represent logical operations then.
Absolutely. So those truth tables that we all know and love in classical logic, they don't really work in intuitionistic logic because it rejects certain equivalences that classical logic depends on.
Huh. Okay. So no more easy cheat sheet, I guess.
Right, exactly.
But if it's so different, then how does it deal with something like arithmetic?
So there's a system called Hating arithmetic, or HA, which is like the intuitionistic version of Peano arithmetic.
Okay.
And what's interesting is they use the same axioms,
Okay.
but the underlying logic of HA is, of course, intuitionistic.
So like same ingredients, different cookie method.
Yeah.
Does that mean it leads to different results then?
It does, and this is a simplified example,
Okay.
but in Hey A, you can prove that every natural number can be written as either 2 times k or 2 times k plus 1, where k is another natural number.
Right.
Seems pretty obvious, right? But you can't actually prove this as directly in classical arithmetic.
Okay.
And so AA arrives for those sorts of finer distinctions because it's really focused on how you construct that proof.
That's interesting. So even though they have the same axioms, because the logic is different, they kind of have different expressive power?
Right, exactly. And it turns out they can actually be translated into each other in a way that preserves consistency, so they have the same strength in a sense,
Uh-huh.
but they emphasize different aspects of mathematical reasoning.
So it sounds like in intuitionistic logic, the journey is as important as the destination.
Yeah,
It's not just what you can prove, but how you prove it.
exactly. And so that has really interesting implications for philosophy as well, especially when we're thinking about the nature of truth
Oh, for sure.
and the relationship between logic and mathematics.
My brain is already starting to hurt a little bit.
Yeah,
But I am intrigued.
okay.
Where do we go from here?
So we've been talking about how intuitionistic logic changes the rules of the game, especially when it comes to proof. But there are kind of two more areas we need to explore to really understand the implications of it. And those are proof theory and
Okay.
semantics.
Proof theory. Okay. I'm not going to lie. I hear that term and I get a little bit intimidated.
Yeah.
Is it just like about like finding proofs?
Well, that's part of it, but it's much more than that. It really dives into the structure of proofs and analyzes the rules that we use to derive them
Okay.
and explores like what kinds of statements we can even prove within a given system.
So it's like meta-analysis of proofs.
Exactly.
We're not just proving things, we're analyzing the act of proving.
Precisely. And so when we apply that lens to hating arithmetic, we see some really interesting features that emerge. So for example, remember the disjunction property we talked about earlier?
Yeah, like if you can prove A or B in HA, you can actually find a proof for A or a proof for B.
Exactly. No waffling, no waffling. And there's a related property called the existence property, which says that if HA proves there exists an X such that A of X,
Right.
you can actually find a specific term, call it T, that makes A of T true. And so both of these properties really highlight this constructive nature of intuitionistic logic.
So they're not just like abstract possibilities, they have concrete counterparts.
Exactly.
That must be appealing to certain types of philosophers.
Absolutely. But proof theory is only one side of the coin.
Oh,
To
Okay.
really fully grasp intuitionistic logic, we also need to consider semantics.
Semantic. I thought we were already dealing with like symbols and logic. What more meaning could there be?
Well, so in classical logic, we often rely on simple truth values, like true or false, right?
Right.
But in intuitionistic logic, things get a bit more nuanced. We use tools like Kripke models and Beth models, which leverage the idea of possible worlds.
Possible worlds. Now, hold on. That sounds a lot like, modal logic.
Yeah, it might sound familiar, but it's used in a very specific way in intuitionistic logic. So imagine a network of these interconnected worlds,
Okay.
and each world represents kind of a different state of knowledge.
Okay.
And you can move from one world to another, and as you do, you might gain more information, but you can never lose information that you already had.
Okay, so I'm picturing like a network
Right.
with different like bubbles of knowledge.
Exactly. So how does truth work in this kind of system? Well, a statement can be true in one world, but not in another, depending on the information available in that world. So for example, let's say P represents the statement, it's raining. In one world, you might be inside your house, you have no idea what the weather's like.
Right.
So P wouldn't be true in that world, but then in a connected world, maybe you stepped outside and you felt the raindrops.
Right.
Now, P is true.
So it's all relative to the specific knowledge of
Exactly.
that world,
Exactly.
not about some sort of objective universal truth.
Right. And so this framework allows us to analyze how the meaning of logical statements kind of evolves as we gain more knowledge, but it also allows us to see how some of those classical laws, like the law of excluded middle, can break down.
Oh, okay. Give me an example.
So let's take that same example. It's raining. In a Kripke model, there could be a world where you simply don't know if it's raining or not.
Okay.
So neither P or not P is considered true in that world. And because truth in these Kripke models can only flow upwards, so as you gain knowledge,
Okay.
this means that P or not P, that law of excluded middle, doesn't hold in that model.
Even though classically it would.
Exactly.
Wow. Okay, so even though we know, like, intuitively P or not P, it seems to make sense.
Yeah.
The Kripke model shows us that, well, it doesn't necessarily have to be the case.
Right, exactly. And Kripke models and Beth models give us this really powerful tool to visualize and analyze the subtleties of intuitionistic logic in a way that truth tables just can't capture.
I'm starting to see why this is so influential in philosophy, particularly for people who are concerned with, like, epistemology and truth.
Exactly.
It really makes you question some assumptions that you didn't even know you had.
Exactly. It pushes us to rethink knowledge and provability and even the fabric of logical reasoning. But there's one more concept that we need to talk about to really complete this picture, and that's realizability.
Realizability. Okay, I've heard that term thrown around a lot.
Yeah.
Never really fully grasped it, though.
It's a fascinating concept, especially for a philosopher like you, because it connects truth to this idea of algorithms
Okay, now that's interesting. I like
or
algorithms.
computable procedures.
Okay, tell me more. So realizability, it connects truth to algorithms. I mean, for me, I'm a philosopher, so I tend to think about truth in these like abstract terms.
Right.
So how does that work from this computational perspective?
So in realizability, the truth of a statement isn't just about whether it's like abstractly true or false. It's about whether you can construct an algorithm or like a computational procedure that realizes that truth.
So it's like, show me the code.
Exactly.
If you can write a program to demonstrate it,
Yeah,
then it's realizable and therefore true.
exactly. It's a very concrete
Yeah.
and constructive way of looking at truth. And in the context of assay-hating arithmetic, we use numbers as kind of stand-ins for these algorithms.
Wait, numbers as algorithms, how does that even work?
So think of each number as like a code that represents a specific algorithm. So when we say a statement is realized by a certain number, we're saying there's an algorithm represented by that number that verifies that statement.
Okay, that's a lot to wrap my head around.
Yeah.
But how does that apply to more complex statements? Not just simple ones.
Right. So let's say you have a statement like A and B.
Okay.
In realizability, this statement is considered true if there's a number that codes for an algorithm, and when you run this algorithm, it spits out two new numbers, one that realizes A and one that realizes B.
Oh, okay, so it's like a chain reaction of algorithms.
Right.
Each one sort of verifying a piece of the bigger statement.
Exactly.
This really drives home this idea that intuitionistic logic is really about computation.
Yeah.
It's not just abstract thinking, it's about what can be demonstrated through algorithms.
Exactly. And it raises some really interesting philosophical questions like, does that mean that anything that's not computable is not true?
Right.
What are the limits of computation when it comes to understanding truth?
Big questions. No wonder realizability causes a lot of debate in the philosophy of math.
For sure.
What about things that we talked about before that weren't intuitionistic principles,
Right.
like Markov's principle. Does that work here?
So that's where things get really interesting because even some principles that aren't provable within HA can still be realizable. So for example, Markov's principle, while not intuitionistically valid,
Okay.
it can be realized using a kind of unbounded search algorithm.
So even though it's not provable, we can still demonstrate it algorithmically.
Right, and there's a really powerful theorem called Nelson's theorem that basically says if you can prove a statement in HA from a set of formulas that are all realizable,
Okay.
that statement itself is also realizable.
Okay, so it's not completely separate from HA.
Right.
They're connected in a way.
Exactly.
So realizability gives us a different way of thinking about truth in math that really emphasizes this computation and this constructability.
Absolutely. And this interplay between these different notions of truth and proof and computation is what makes intuitionistic logic so fascinating and so rich, especially for a philosopher like you. It really challenges us to re-examine like our most basic assumptions about logic and math and even about the nature of knowledge itself.
It's definitely been a whirlwind tour.
Yeah.
Rejecting the law of excluded middle, possible worlds, realizability, all this stuff.
Yeah.
I'm starting to understand why this is such a big deal.
Yeah.
And for anyone out there who's listening and kind of wants to, push the boundaries of their own thinking,
For sure.
I highly recommend taking a closer look at intuitionistic logic.
Yeah. We've got some great resources in the show notes, too.
Awesome. So until next time, keep questioning, keep exploring, and keep those philosophical gears turning.
Absolutely.